Jack is going to present the results of the working group on directionality of the ground motion. Jack, welcome.
Okay, great. Good morning. So I'm here to present the results from this directionality study efforts. This work is done in large part by Shrey Shahi, who's in the audience and is just about done with his PhD at Stanford, and with the kind of multiple reviews throughout the process by the working group members who are listed there at the bottom through a series of conference calls and meetings to kind of review these results as they evolved. So I guess motivation here is that in some engineering circles there's interest in looking at response spectra that are the maximum response spectral value observed over all horizontal orientations of a ground motion. And so, for example, the 2009 year provisions specified that they wanted ground motion hazard maps defined for this maximum direction spectral acceleration, which is different than what the NGA models are developing as the base models are using this ROT-D50 measure. So we are looking at the differences between those two measures for ground motions and aiming to develop modifications to convert between those two definitions of ground motion response rate. In some sense, very similar to the damping scaling factors that Sanaz was talking about earlier. And so that's kind of a primary issue is how do those two predictions relate, or those two ground motion values relate to each other. There are some secondary issues regarding kind of directional changes with period for a given ground motion and things. I'll show you some additional results of that type that are important for kind of engineering applications of these other max direction response spectra. So just for some background, you've heard some of the terminology already, but I'll give you an extra minute or two of some background on these. So these are plots of 1 second oscillator responses for two different ground motions. So this is relative displacements if you looked down from above on an elastic oscillator that's free to rotate in any direction. And the maximum amplitude of an oscillator in a given direction, then when modified by an omega squared factor, would be a pseudospectral acceleration. These plots are just normalized to be a maximum at the largest extent of the sorry, they take maximum values of 1, so they're normalized. And so you can find a maximum direction spectral acceleration by just looking at the maximum displacement over all these different orientations. If you were to look in a specified orientation, that would be the response of an elastic oscillator in just that single orientation if applied to if subjected to a ground motion in that orientation, a single component ground motion. So looking at that right figure, so the orientation of the ROT-D100 spectral acceleration, which is the 100th percentile of spectral accelerations over all possible orientations, would be in this direction a little bit less than 90 degrees for that right ground motion. The minimum orientation would be the 0th percentile. That would be in this orientation here. And then the ROT-D50 orientation will be the median spectral acceleration over all orientations. And that's what's the prediction being made by the ground motion prediction equations. And then just a note here is that in a case like this where the projection of response along this ROT-D50 orientation is going to be, the maximum displacement is going to be this maximum displacement here just projected over to that 300-degree plane here. And in a case like this, the ROT-D50 orientation is going to be 45 degrees away from the maximum orientation. And so you get a right triangle here with sides of length 1 and a hypotenuse of length square root of 2. So your ROT-D100 can be at most kind of square root of 2 times the ROT-D50 spectral acceleration. That's a bounding value. And then thinking about a case on the left where the responses are a similar maximum in all orientations, your ROT-D50 amplitude is about equal to your ROT-D100 amplitude, so you have a lower bound of 1 on the ratio between those two. So everything goes between 1 and square root of 2 in terms of the ratios we're looking at. Okay, so then mathematically what we're thinking about here is that if you're interested in a ROT-D100 spectral acceleration, well, you could just multiply and divide by a ROT-D50 spectral acceleration. So that's the right-hand side here. Then you could take logarithms of both sides, and I could say that the logarithm of ROT-D100 spectral acceleration is the log of this ratio plus the log of ROT-D50 spectral acceleration. And the reason to decompose it like that is that this ROT-D50 spectral acceleration is what's being predicted by the model developers, and so they can do a very careful study of magnitude, distance, VS30, other dependence on those, say, ROT-D50s. Then this study aims to just provide a prediction for that first term in this equation, and this is going to be a much simpler prediction as we'll see in a second. So So the base ground motion prediction model catches all of the very complex magnitude, distance, site condition scaling, all of that type of stuff. The conversion to ROT-D100 is relatively simple, potentially even a constant as a function of period. We'll discuss that in a little bit. And this decoupling leaves these two models that can be a little bit independent, and we don't have to reproduce all of the careful study that goes into the ROT-D50 model, which would be necessary if you didn't decompose it into a ratio like this. Okay, so we'll talk about a number of results related to these ratios. I don't think I'm going to talk through all those right now. In terms of data, so we're using the NGA West 2 data set, of course, to take advantage of that nice high-quality data. And then rather than do our own screening of the data, we took subsets of the data that were identified by the various modelers as of about a year ago. So we have a draft version of that so that we don't have to revisit the thinking that they were putting into this. And so then for those data sets, we recomputed our own response spectra. We wanted a couple other values than were in the flat file. So we computed 5% damped spectral accelerations at 21 periods rather than all the periods. But we recomputed spectral accelerations in 1 degree increments over all unique orientations of each ground motion. So that's the types of things shown in that little figure on the bottom right. And that was the data set we started from. Just to show you what things look like, so I showed you one ground motion, the ROT-D100 and the ROT-D50 values. So in this particular ground motion, the ratio of ROT-D100 to ROT-D50 is 1.4 or square root of 2. In other ground motions, it's different. And that ratio also depends on the period of this oscillator. So this is a 1-second oscillator, but we do the same thing for all the other periods of interest. So the types of data, just looking at the complete data set, looks like this. So this is a 0.2-second oscillator, and then the x-axis is ROT-D100 over ROT-D50 response vector going from 1 to square root of 2, and then just a histogram of how many ground motions in the data set there are. I'll note all of these results are from the Abrams and Silva data set, but the figures are essentially indistinguishable if you use other developers' data sets for these same figures. So at 0.2 seconds, we see kind of most of these ratios falling between 1.1 and 1.2. At 1 second, the histogram shifts a little bit towards larger ratios being more likely. Then what we're looking for, if you remember, we want kind of the logarithm of these ratios and then a mean value, which we're estimating using a mixed effects regression. But the kind of the geometric mean of these ratios that comes out of that mixed effects algorithm is shown here. So for the 0.2 second period, we end up with a ratio of about 1.2, and that's plotted with this circle. And then at the 1 second period, the geometric mean ratio is a little bit larger, and you can see that period dependence trend is relatively continuous across the full range of periods we're interested in. Okay, so that's the kind of the geometric means of this ratio. Here's a plot of that those same numbers compared to a number of previous models. So a number of people have studied the same or similar ratios. So those are all superimposed on this figure. One note here is the y-axis is flipped just slightly. So this is ratios of ROT-D100 spectral acceleration to GM ROT-I50 spectral acceleration, because the previous models were generally comparing that ratio. We put our plot on the same figure by using a conversion between ROT-D50 and GM ROT-I50 that Dave Bohr developed. So the GM ROT-I50 and ROT-D50 response vector are very similar in a geometric mean sense at short periods, and there's a 5 or 6% difference at long periods. So this ratio is a little bit higher with this y-axis than in the previous figure. But so the things to note, I guess, is that all of these models that have, anybody who studied this has found quite close agreement in these ratios, although there is significant overlap in some of the data sets here. There's also a quite strong period dependence, and so the ratios are certainly period dependent. And then the question is there additional magnitude, distance, site condition, directivity dependence in these ratios that's not captured by the ROT-D50 based GMPEs? And then one other note is added on here is the suggested ratios of this type from the NIHR provisions in 2009 that differ quite significantly from all of the studies. And so we have guidance that those need to be revised to be treating the data a little bit more appropriately. I won't get into details of that. Okay, so then these are ratios just for the entire data set considered. So a question was, well, is there magnitude distance dependence and so on? So here is a plot of, so the y-axis is again ROT-D100 over ROT-D50 response spectra, ranging again from 1 to square root of 2. Each dot on this figure is a single ground motion, and the left figure is for 0.2 second response spectra, the right figure for 1 second response spectra. And now the x-axis is the closest distance for each of those ground motions, so looking for some distance dependence. So you see there's certainly not a strong, clear trend here. There is a slight trend here. So we played with a number of kind of moving average fits and things to try to see if there's anything hidden in all this data. There is a very slight trend as indicated by these red lines that are distance-dependent regressions. It doesn't have a big practical impact. You can see it here by comparing either the dashed black line, which is just the overall geometric mean, versus the red line, which is a regression prediction. There's a difference of 1 or 2% in this ratio in close, which is kind of where people are interested in this. Another way to look at this would be as follows here. So the black line is the overall geometric mean of the data set. The dashed red line is the results from using those regression predictions on the previous slide, period by period at a distance of 0. So we've provided both a kind of an overall geometric mean prediction, so those black, the numbers corresponding to that black line are tabulated, and then also a simple functional form that's linearly dependent on distance. We provided the A0 and the A1 coefficients from this equation that would produce that dashed red line. So a distance-dependent model is available. That kind of difference is I question the practical value of that in almost any application, but if you're interested, it's available. This is also consistent with previous studies. I know Jenny Watson-Lamprey and Dave Bohr in particular studied this as well as other parameters and noted slight dependencies of the same type, but also judged that it's unlikely to be of practical importance in almost any situation. So I have similar plots like this for magnitude, the various directivity parameters that have been considered in those directivity models. We tried to do some kind of radiation pattern dependencies. This is the strongest trend of any of those plots. If you'd like to see the other plots, we can pull them up though and show them to you. So the only potential predictor parameter that we would suggest anybody consider would be distance, but we note that the effect is quite small. Okay, another thing is the standard deviations of these ratios. So again, kind of looking back to that mathematical model. So we have the primary ground motion prediction equation and then this ratio here. So this is the fits here. We're all done doing mixed effects regression. So you get a within event term and a between event term. So this is example numbers for 1 second response spectra. The other periods, the standard deviations vary, but within 20% or something of this, it's relatively constant. If we kind of roll those standard deviations in with, for example, the Campbell-Bazorgnia 2008 NGA model, so there's a slight mismatch because it's not a ROT-D50, but you'll see that it doesn't matter too much, I think. So the within event and between events standard deviations are shown there. If you roll these all up, the ROT-D50, or more precisely the GM-ROT-I50 standard deviation, was 0.623 from Campbell-Bazorgnia. If you roll in these new sigmas and assume everything's uncorrelated, you get to 0.629, so a 1% increase in standard deviations. So again, I think it's basically noise in the overall model, and we provide these taus and fees in the report, but for most practical purposes, I think it's just fine to assume that the ROT-D100 spectral accelerations are going to have the same log standard deviation as ROT-D50 spectral accelerations, and you really only need that ratio of the geometric means to do any sort of conversion. And that's implicitly what's done in the ASCE 7 hazard maps, where the factor is applied after the fact rather than rolled into the hazard analysis, which is only a reasonable thing to do if the standard deviations aren't changing between definitions. Okay. So that's kind of the key numbers that are needed to use this stuff in any sort of hazard analysis. But with respect to engineering use of ROT-D100 spectral accelerations, we looked at a couple other things. So one was the orientations of these ROT-D100 spectral accelerations. Are there preferential orientations in which the larger spectral accelerations are seen? So what we looked at was if we had a rupture, and we knew its strike, and then we had a site where we had a ground motion recording, and we knew the orientation of the ROT-D100 spectral accelerations for that particular recording, we took an azimuthal angle alpha we took an angle alpha as the ratio, as the angle between the strike orientation and the orientation of rote D100. Okay, and so just as an example, here's a ground motion. There was a near fault ground motion. It's about 5 kilometers from the Imperial Valley rupture, 1979, and just to illustrate, so at 1.5 seconds, an elastic oscillator displacement would look like this. So the maximum spectral acceleration would be in this orientation, just approximately in the fault strike parallel orientation. And so we would have an alpha here of about 10 degrees or so. At the same ground motion for a 3-second oscillator, the maximum response is in a much different orientation, approximately strike normal. So we would have an alpha of approximately 90 degrees in a case like that. And so we wanted to look at the kind of tendencies in those orientations as well as the differences in the orientations period by period, because that has some important implications for engineered structures that are sensitive to excitations at multiple periods and in multiple orientations. Okay, so here is how we aggregated up the data. So these are histograms versus alpha. So each one of these plots, the x-axis is alpha running from 0 to 90. So 0 is strike parallel, 90 is strike normal. And then each one of these panes is an individual pairing of closest distance and magnitude. So up here we have magnitudes from 5 to 6 and closest distances from 0 to 3 kilometers. So there's no observations in that bin. Going down to, in the lower right, distances of 30 to 40 kilometers from magnitude 7 to 8 earthquakes. And so we were looking in various magnitude distance combinations. Is there a tendency towards preferential orientations? And so staring at these a bunch, we decided on a pattern that kind of, and we played with these magnitude and distance boundaries quite a bit as well to try to separate out any changes in behavior. So we saw that within 5 kilometers, you have these histograms that are tilted towards the 90-degree orientation. So we have preferential observations of rote D100 spectral accelerations in the fault normal direction, or approximately the strike normal direction. Outside of 5 kilometers, these histograms are quite flat in general. And so for distances of larger than 5 kilometers, we didn't see any sort of preferential orientation with distance. And then looking across these rows, we didn't see any significant differences. And so we didn't identify any magnitude-dependent trends in these orientations. Okay, so I should note also this is a histogram of these orientations across multiple periods. So a single ground motion has different orientations at different periods, and all those orientations were used, kind of rolled into here across the 21 periods we were interested in. So another way to look at this would be to split this out and look for period dependence in these orientations. So given that there was no magnitude dependence that we could observe through various plots, this is now histograms of data pooled across all magnitudes in the large magnitude database only, I should say. Now each pane is a different oscillator period, so from 0.01 seconds up to 10 seconds. And this is only ground motions within 5 kilometers of closest distance to the rupture. So outside of 5 kilometers, similar plots don't show any interesting patterns. So here, what we saw was that at periods of a half second and longer, you get a preferential orientation towards alpha equals 90, or strike normal orientations. For periods less than a half second, those histograms appear to be essentially uniform, so we didn't see any sort of preferential orientations at shorter periods. Okay, so to kind of summarize those plots, and we have some other permutations of them, but those are kind of the most interesting looking ones. There is some distance and period dependence on these orientations, and again, these are really confirming previous work by some of the authors that were noted earlier in that comparison. So the distributions of these orientations tends towards fault normal when you're within 5 kilometers and you have periods of a half second or longer. So we definitely see that in the data, but that is not the same thing as saying that maximum, that rote D100 spectral acceleration is always fault normal. So there's plenty of in-close ground motions at long periods where the rote D100 orientation is closer to strike parallel than strike normal. So there's a tendency, but it's not an absolute rule. Outside of 5 kilometers or at short periods, the distribution of these orientations appears to be apparently uniform over all possible orientations. Okay, magnitude didn't appear to be important. Directivity parameters, we couldn't find any strong distinctions there. Okay, then the last kind of class of things to talk about is these orientations and how they vary with period for a single ground motion. So kind of that same example where the 1.5 second spectrum and the 3 second spectrum, the maximum direction spectrum are in quite different directions, even for a single ground motion. So some things we looked at here is maybe I should stick on this slide for one more second. So in this case, between 1.5 seconds and 3 seconds for this particular ground motion, those two D100 orientations differ by approximately 90 degrees. So we can do the same calculation for the whole suite of ground motions and for all pairs of periods in our data set. So these are plotted histograms of the x-axis is difference in orientation of the two alphas for two different periods, and then the two periods are indicated at the top of the figure. So for all the ground motions in the data set, 1 second response spectra and 2 second response spectra, the difference in orientation of the maximum direction spectrum, and we have a histogram plotted. So we've got that difference of a factor of 2 in period. It's still more likely that you'll see the max direction orientations in the same direction, so a difference in alphas of 0. That's more likely than that you would see those max direction orientations in perpendicular directions, but there's not a tight clustering at 0 here. So for different period pairs, so the top row shows period pairs that differ by a factor of 2. The bottom row shows period pairs that differ by a factor of 5. So the correlation in directions breaks down a little bit in the bottom row. The left column is kind of longer periods, and the right column is shorter periods. There's a little bit of a difference and a tendency maybe for the shorter period cases to group a little bit closer to common orientations. Okay, so we've got in the report there's provided both kind of tabular data providing values of these histograms, as well as a parametric fit to this distribution that's indicated by that red line, so that if people are interested in how these orientations might differ, they'd have some basis by which to quantify that. Okay, then, so one issue is how much different are those orientations? And then the second issue is, well, maybe even if the orientations differ by 20 degrees, the amplitudes at a given orientation are both quite close to the ROT D100 orientation, even if it's not exactly the ROT D100 spectral acceleration. So taking this example figure to the right for just a moment, we first come in and find the ROT D100 orientation for a given period. So this is a 1 second response case. And then we move away from that orientation in 1 degree or in a few degree increments and look at how the response spectrum decreases away from that orientation. And we do that over kind of all the ground motions in the database and look at geometric mean values. And then actually these are plotted relative to the ROT D50 value rather than the ROT D100 value. So over here on the left side of the plot, we're at an angle relative to the ROT D100 orientation. So on the left side, you're actually at the ROT D100 orientation. And on the right side, you're perpendicular to the ROT D100 orientation. Then the y-axis is the geometric mean value of the spectral acceleration in that specified orientation relative to the ROT D50 amplitude. So at about 45 degrees, you're hitting about the ROT D50 value, and so these ratios are about equal to 1. When you're over on the left side, you're at the ROT D100 orientation, so these values are exactly the ROT D100 to ROT D50 ratios. And then over on the right side, these are the ROT D0 to ROT D50 ratios. So the idea here is that as a function of orientation, you could amplify or de-amplify your response spectrum prediction if you knew where ROT D100 was, and this is shown for 3 different periods. Okay, so this can be combined with the previous slide saying how far different from the ROT D100 orientation would you be at a given period, and you can come up with some predictions. And let me show you first kind of raw data, and then second, some predictions like that. So here, just to take a particular ground motion, so this is a ground motion chosen somewhat at random, except that it's close in. So there's 4 response spectra we can think of that you could compute. There's more than that, but 4 potentially interesting ones. So you could compute a ROT D50 response spectrum. You could compute a ROT D100 response spectrum. You could compute the response spectrum in the fault normal direction. Or you could compute, this dashed black line is the response spectrum in the orientation at which the 1 second response spectrum is equal to the ROT D100 response spectrum. And those are all different, although that's not always appreciated. So just some comparisons. So first, the fault normal response spectrum doesn't look like the ROT D100 response spectrum. Sometimes it's similar, but at some periods it's quite a bit lower. And then another way to look at this would be if we're going to, instead of picking the fault normal orientation, here we'll pick the orientation at which the 1 second oscillator will respond in its maximum amplitude. So at this 1 second period, this dashed black line is exactly equal to the ROT D100 response spectrum by definition. But now as we move to another period, we don't switch orientations to find the ρd100. We just keep that fixed orientation. And so you can see that at other periods, because the ρd100 orientations vary period by period, that spectrum is going to be lower than the ρd100 response spectrum in general. And so, so those are different things you could compute. And using the couple slides earlier, I won't go into completely the details, you can make predictions like that. So here is now a hypothetical case, a magnitude 7 at 2.5 kilometers on a rock site. And this is predictions of a ρd50 response spectrum, a ρd100 response spectrum, which just uses our factors and multiplies directly up, a strike normal and a strike parallel response spectrum, and those are computed using the histograms of known histograms of orientation of ρd100. So because we know that the ρd100 amplitudes tend to be closer to fault to strike normal in this configuration, that response spectrum is a little bit higher. So those are all things that could be computed. And then over on the right, we've kept the ρd50 and ρd100 response spectra the same. And then it's a little hard to see in here because of the overlap, but we have also response spectrum plotted in the orientation of the 1 second ρd100 value or the 3 second ρd100 value. So at either 1 second or at 3 seconds, these spectra are equal to the ρd100 spectrum, but they come back down at other periods heading towards the ρd50. And this may be splitting hairs for some people that aren't so interested in this, but what we're trying to provide models for and some commentary for is that ρd100 response spectrum is not observed in any single orientation of a given ground motion. And when engineers want to use that ρd100 response spectrum as amplitudes of shaking in a particular direction as they're modeling a building, that's not something that any of these models actually predict would happen. There's various other response spectra that might be representative of response spectra that a building could observe. But simply using a ρd100 prediction and making that prediction for a whole bunch of periods and drawing a line between them, there's no unique orientation in which that's observed. And so we wanted to provide the kind of alternate underlying models and some commentary on that. OK, so to wrap up, I first showed you kind of geometric mean ratios of ρd100 over ρd50 values. They're generally consistent with previous studies, with the distinction being that our denominator is ρd50 instead of rodi50. So there's, especially at long periods, there's a difference of a few percent to 5%. But once we account for that difference using Dave Bohr's predictions, we see consistency with those previous models. So we've provided ratios in this format, but there's nothing real surprising there. Those ratios are clearly period dependent, so we provided period dependent ratios. They're weakly distance dependent, and so we've provided an option for that distance dependence if it's of great interest to somebody. There was not clear dependence on other properties that we've seen so far. We're tying up a couple loose ends with regard to that with some review comments that we received, but there's not much interesting going on there. The orientations of the ρd100s, outside of 5 kilometers, those orientations are essentially uniformly random. Within 5 kilometers and at longer periods, there is a tendency towards a fault normal orientation. We've tried to quantify that. And then the second part of the presentation was talking about these orientations. The orientations of ρd100 response spectra vary with period for a given ground motion. And so computing response spectra for a given orientation is complicated when you want to jump to this ρd100 definition. But if you're tied to the ρd100 max direction definitions for engineering applications, we try to provide some models that'll help quantify those differences a little bit more carefully than we were able to do in the past without that type of study. So with that, thanks again to our technical review team, and I'm happy to take questions.
Thank you very much, Jack. Very good. Questions for Jack regarding orientation? Zio.
Just wanted clarification. The ρd100 is the orientation based on peak ground displacement, not a spectral displacement, right? It's a PGD based.
No, it's spectral displacement based.
So it will change with different periods?
Yes, it does.
But so there is no specific definition ρd100, like for one particular period, or it's just
there is a specific definition. There's not a unique orientation of a multi-component ground motion that will be the orientation of ρd100 at multiple periods.
And then you go back and calculate the spectral acceleration for that particular orientation.
That's right.
Okay.
Yeah.
More questions for Jack?
Thanks. This is sort of a generic question across the morning. We talked about near BAMP factors. We talked about damping ratios, adjustment factors for those, and now we're talking about the rotation correction factors. And particularly when we're talking about them with regard to their application to the building code, which is going to be more than just California or Western U.S. active tectonic regions. I did hear during the damping factor that they were particularly applicable to the active tectonic regions, California, Western U.S. Are there going to be limitations here when we start applying these to the building code for any of these things?
Sure. So to take the example of Eastern U.S., I mean, this study could be repeated exactly for Eastern U.S. data. I have a little bit of that, and we're trying to do a little bit of that as part of the NGAEs project. So, I mean, I think in general, whenever you're trying to apply these models in a place where they weren't calibrated, it requires some careful thought and not just blind application. I'll say specifically for this, in my limited look at the Eastern U.S. data, the ratios are quite similar. My impression, especially looking at the lack of dependence on magnitude, distance, whatnot, is that these are really kind of just a random vibration phenomenon and not strongly seismologically driven. It's just a matter of how long you shake this oscillator forward that it has a chance to respond in multiple directions. So in this particular case, I wouldn't, at first glance leaves a lot of sleep over applying these elsewhere. But I think that as part of NGA East in particular, we'll be able to be more precise than that in time for national application of things like this.
I'm curious if when they do get applied to the building codes, whether there's going to be a distinction as to where you are in the country, whether East Coast or West Coast.
And for damping also, the plan is that SONAS is going to look at, in the next few months, for the Central Eastern U.S., same damping ratio to see if they're different or the same. Okay. Any other question for Jack?
I just want to get some clarification on how these work their way through to the design structure. One scenario is that you use the directivity in the ground motion prediction equation to develop S sub S and S sub 1, and then you use that through the amplification factors to determine a design response spectrum. And then you filter that through the PSHA methodology. So if you have a fault like the Landers fault, you consider that very rare, and so you end up with a low design. The other thing is if you look at the fault and want to make a deterministic response spectra, that you use this maximum directivity, and it seems like you could get very different answers. So what is the intended... How do you intend to get to the response spectrum that a structural will see?
I think all of these models are used in PSHA calculations or in deterministic hazard calculations. In either case, you're going to specify seismological conditions you need predictions for, and then the question is, what are you trying to predict? Are you trying to predict a Rho D50 response spectrum, or a Rho D100 response spectrum, or a 5% damped response spectrum, or a 2% damped response spectrum? And so all of these models are going to require similar inputs and similar inputs to what's done in current building code hazard calculations. And we're just aiming to provide, informed and refined predictions of the desired output. So I don't think there's any difference in the way it would be applied. It's just if you would like a prediction of Rho D100 response spectrum instead of Rho D50 response spectrum, this provides the needed inputs for that required output.
Great.